Suppose, though, that the order does not matter. Suppose it doesn't matter which, when you're doing a competition, first, second, and third place matters. But let's suppose that you are selecting 3 out of 4 books, and we'll just title those books A, B, C, and D. It doesn't matter which order you pull them off the bookshelf. Whether you pull the A, then the B, then the C gives you the same 3 books as if you pull the A and then pull the C book next and then the B book last. Or pulling the B book first and then the A and then the C. The order doesn't matter. You're still going to get the same stack of 3 books. This is referred to as a combination. Remember, a combination, it is not important. The order of objects selected is not important. That is a combination. Combination starts with the letter C, so we would write combination as NCR. And the way you figure out NCR is that in this particular case, since we have 4 books to choose from, and there is a book D, it's not listed in the illustration, but it does exist. We have 4 books, but we're only selecting 3 of those books. So we would write that as 4C3. 4 books to choose from, but we're only selecting 3 of them. You would figure this out by taking 4 times 3 times 2, so starting with 4, counting to the first 3 numbers. But then you're going to divide by the 3 factorial. And remember, 3 factorial means 3 times 2 times 1. So you would have 4 times 3 times 2 divided by 3 times 2 times 1. And sometimes when you get very large combinations, even scientific calculators won't have enough spaces to fill all the numbers needed to show the number of combinations. So you can start canceling out some of the numbers that are the same. So the 2's could cancel out and the 3's cancel out, meaning that you're left with 4 over 1 or just 4. So there's actually only 4 different unique stacks of books that you can get from 4 books chosen 3 at a time. A situation that you may run across in real life is playing a card game. How many different ways are there to choose 5 cards from a standard deck of 52 playing cards? So you're playing your favorite card game, and you get dealt 5 cards. The order you get dealt those 5 cards in most card games does not matter. So this is a combination. We would write this as a combination of 52 cards, a combination of that, choosing 5 of those cards. So that would be 52 times 51 times 50 times 49 times 48. And then we would divide that by 5 factorial. That's 5 times 4 times 3 times 2 times 1. And again, if you try to type all that into a calculator, you're going to get some very large numbers. Particularly, it may not, if you have an 8-digit calculator, it may be too large to fill it up. So let's start canceling out some numbers. For example, we could take the 5, and 5 goes into 50 10 times. So the 5 would be canceled out. 5 goes into 50 10 times, so change the 50 to a 10. The 4 can go into the 48 12 times. The 3 can go into the 12. You can reuse a number that you canceled out. The 3 can go into the 12 4 times. And then the 2, and I'm going to use a different number this time. I'm going to use the 52. The 2 would go into the 52 26 times. And honestly, it doesn't matter which one you choose, because by the time you multiply it out, it's all going to be the same answer. So now we're going to have 26 times 51 times 10 times 49 times 4. And when you multiply all that out, you get 2,598,960 possible combinations of 5 cards from a standard 52-card deck. So again, you would do this, a combination, if the order is not important. So a lot of times the challenge becomes determining whether the order is important or if the order is not important. If the order of the object selected is important, then it is a permutation, which means there won't be any division. If the object of the order is selected without regard to order, in other words, the order does not matter, then this is a combination. So 25 students write their names on slips of paper, then 3 different names are chosen at random to receive prizes. Determine whether each situation involves permutations or combinations. Choosing 3 people to each receive a no homework coupon. So in this particular case, since the first 3 people chosen all get the same prize, it doesn't matter. It doesn't matter whether you get chosen first, second, or third, you still receive the same prize. So this is a combination because the order does not matter. So this would be 25 total students, a combination selected 3 at a time. So that would be, again, this is a combination. That would be 25 times 24 times 23 divided by 3 factorial, 3 times 2 times 1. And let's see, I could take the 3, goes into 24 8 times, and then I can reuse that 8 with the 2. That would be 4 times. So I would have 25 times 4 times 23 divided by 1. That is 2,300 combinations. Part B, choosing 3 people to receive 1 of each of the following prizes. First prize gets a new graphing calculator. Second prize gets the no homework coupon, and third prize gets a new pencil. This time the order matters because there's a big difference between getting a graphing calculator and a pencil. So this is going to be a permutation. So a permutation would be 25 permutations, selecting 3 of those. So no division on this one. This is just 25 times 24 times 23. And when you take 25 times 24 times 23, you get 13,800 unique permutations in which the teacher can award these prizes.